In this section, we will cover the Euler method and one of its most popular extensions, the Runge-Kutta method. Now, the Runge-Kutta method is actually quite simple to formulate and implement, which makes it applicable to a wide range of dynamic systems. In fact, the way we formulate the problem for both linear and nonlinear systems is almost identical, which is a huge advantage. Because it is so general, you will find some version of the Runge-Kutta method in almost any kind of computing package, including MATLAB and MathCAD. This is not true for the other methods that we've covered so far. So it's a good tool to have in your arsenal if you want to take advantage of some of the more sophisticated numerical simulation tools that you have in some of these programs. Okay, so first let's look at Euler's method and its key assumptions. Let's start by looking at the displacement over time. So as usual, at time ti, we'll assume that we know the displacement. We'll also assume that we know the velocity of the system at that particular point. And we'd like to find the displacement at some time ti plus 1 after we've stepped over this time interval, delta t. Now, the fundamental assumption that Euler's method is going to make is that we can project the velocity over this time interval to get to the subsequent displacement I plus 1, ui plus 1. And that's basically it. So let's look at how that might look like for a basic linear first order differential equation. So we have our velocity would be equal to some function of t and u. And in the case of a linear system, we'll simplify that to some constant times u. So what Euler's method says is that first we can get our velocity u dot I directly from that equation of motion. And our known ui. And then we can use the formula for average velocity over delta t to set up our final equations. So in that case, we have the difference between ui plus 1 and ui over the time interval delta t is equal to our velocity, or in other words, a times ui. So rearranging that to put it in terms of ui, we get the following equation. And that is the general algorithm for this method. Extremely simple. If the system is not linear, well, we can just simply replace this with some more general function in terms of t and u. The Runge-Kutta method is simply a more sophisticated version of the Euler method, in that we actually calculate several velocities in the time interval delta t before making the final estimation of ui plus 1. But the setup is exactly the same. We have some known displacement, some known velocity to start with. But in this case, we'll use two time intervals. One halfway, which we'll call delta t over 2, and then the total time interval delta t. The method essentially calculates four velocities. The first one is the same as the Euler method. We'll call that ki1. This velocity is projected to halfway into the interval, where the method calculates a new velocity, which we'll call Ki2. Then using Ki2, it projects again into halfway of the interval. Here it calculates a new velocity, which we'll call Ki3. The method then again uses that calculated Ki3 to project this time all the way to the final point, which we'll call ui plus 1 prime, and calculates a final velocity at this point, which we'll call Ki4. From there, it does a weighted average of all four velocities, weighting the ones in the middle most heavily, and then does a final projection using that averaged velocity to our actual estimate ui plus 1. And so that is the illustrated version of the equations that we see on the right, where we see that ui plus 1 is again the initial u times some weighted average of these four velocities. Notice how the two velocities calculated in the middle, Ki1 and Ki2, get the larger weights. Each one gets a weight of 2, and we divide by 6. And the calculations for each of the velocities are shown below. Notice that Ki1 is calculated exactly the same as in the Euler method. Then Ki2 has the time increased by the delta t over 2. Same for Ki3, and then Ki4 has that time interval increased by delta t. So pause the video if you need to, look over this and understand how this method projects forward. But the idea is that fundamentally this is the same as the Euler method. We're just getting a better estimate of the velocity by averaging several velocities within the time interval delta t instead of just taking the one at time ti. So far so good. However, the way that the Runge-Kutta method and Euler method are formulated, namely with respect to first order differential equations, means that they can't be applied directly to our equation of motion because it is a second order equation. However, there is a way to turn any higher order differential equation into a first order one, and that is through what we call the state space formulation. Now involves some linear algebra and a variable transformation. So we're going to define, first of all, a variable y1. We'll set that equal to u, and then we'll define a variable y2, and we'll make that u dot. That means that we define a vector which is simply y1 and y2, or in other words, u and u dot. By extension, this means that we can also define a vector y dot, which is simply y1 dot and y2 dot. This is the same as saying u dot and u double dot. And so we end up with the following. The first one is simply y2. Right, remember that y2 is equal to u dot. And then u double dot comes from the equation of motion above. Now notice that we need this to be in terms of y, so we can replace the u dot with y2 and the u with a y1. Right, so now we have a y dot that's exclusively in terms of y variables. So we can set up our first order system, right? So we have finally y dot is equal to some function of t and y, right? And that function looks like what we just had there. Notice that this looks exactly like it did before, except now we're using vectors instead of scalar functions. So putting everything in context of the Euler algorithm, we'll start with the general differential equation of u double dot plus some function of u and u dot equal to some loading function. Now this is just a more general way of writing, but notice that for your typical linear system, this f of u might look like, and in that case the Euler solution is the same as before, but again in vector notation. So we take the time interval delta t, we multiply it by our vector function, and we get the next vector in time, where our vector y is what we defined previously, and our function f in a more general form looks like the following. But again, if you were to replace the f with the linear system version, you would get exactly what we got in the previous slide for our f function. The Runge-Kutta algorithm is here. Again, starts the same as the Euler version, and we just replace the scalar values with vectors, but it works exactly the same. So you'll notice that the equations are practically the same, just with the vector form of f replacing the scalar form of f, and the vector form of yi plus 1 and yi replacing the scalar forms. So these two are for your reference in order to implement this algorithm for second order equations of motion. The great thing about this solution and this algorithm is that they are already built in to MATLAB and MathCAD. You see the functions here, and in the next video I will show you how to implement these functions in MATLAB.